now what I would like to worry about at this point in time is the last topic of the chapter, which are aircraft gas turbines or jet engines. So, or jet engines. So what happens now, so I guess the first thing I should say is, why does a plane fly? So if I have a plane, let me see, I have to think about how I'm going to draw this plane. So if I have a plane, here I am, plane, and I have a wing out here and a wing out here. And I have a jet engine, so the engine is mounted here on the plane. What makes the plane go? Is that the jet engine makes it go horizontally. The shape of the wing, so this is your wing. So the shape of the wing, as it goes through the air, it creates a pressure difference, and the pressure difference creates a lift that pushes this up. So the jet engine only is like a reactive force that makes it go this way. The shape of the wing makes it go up. So I'm not going to worry about the shape of the wing. I'm going to worry about this jet. So with the jet, what happens is you have a diffuser. So a diffuser is the opposite of a nozzle. It slows things down. So I have this engine moving through space. So I have my engine going through space. And so from the engine's perspective, air is coming into it. I need to slow it down to build up the pressure. Then it's going to go into the gas, to a gas turbine. So I have a compressor, combustion chamber, into a turbine. The purpose of the turbine is to drive the compressor. And then the exhaust from the turbine is at high enough pressure to go through a nozzle. So it's going to come out and go through a nozzle, and that's what creates the reactive force. So if I look at this, I'm going to start here. 1, 2, 3, 4, 5, 6. So when I look at this, this is what it looks like ideally. And then with a TS diagram, we're going to go isentropically from 1 to 2. So from 1 to 2, there's a pressure increase. As I slow this down, I have the conversion of kinetic energy into enthalpy. So it's slowing it down. So the KE coming in is converted into enthalpy, and which causes a rise in pressure. Then it's going to go through the compressor again, ideally in a reversible adiabatic fashion. All these things have efficiencies with them. And so then it's going to go 2 to 3 through the compressor. Then I'm going to add fuel or heat from 3 to 4. So there I'm adding energy to it. So this is the work of the compressor. Here is WC. So this distance here, this enthalpy rise there is that. So from 4 to 5, when it expands 4 to 5, this WT, so here's the WT, that WT is going to equal this WC. And then I go from 5 to 6, and this is the delta KE. So now I have the conversion of enthalpy into kinetic energy. So it's going, I have a pressure drop, and I'm speeding up. I have the velocity increasing, and so the velocity increases, and that gives me the force to drive this, to drive my eraser jet, my high-class visual aid. So that's what, this is going out with a high velocity, and that's making this go this way. And so I have that. And so now, what we're going to do is, there are a couple of developments for the work and power for the jet engine. And what I found was that the easiest one is the impulse momentum analysis of the engine. The more complicated one is the one that's done throughout the text. And so I think The more complicated one was to show that we could do it from thermodynamic principles and not from impulse momentum. But once I wanted to explain it, it seemed to make much more sense to do the impulse momentum. So if I look at this, the propulsive force is the continuous change of momentum of the gas as it goes through the engine. So we have that. Now let's draw a little sketch to put down these things. And we know that the force is equal to dmv. So the momentum is mv, and the change of this gives us a propulsive force, so we have that. And now what we want to do is look at an engine and put these things in, etc. So that's what we'll do next. So the engine has all this stuff in it. And so I'm going to have here m dot A VI, and VI is equal to V sub t, the velocity of the plane. So the plane's going along, that's what's happening. I have the fuel going in, so I have m dot A RFA is the fuel that's going in. I have the momentum leaving, so I have m dot A times 1 plus RFA times VE. And so this is the momentum out. And this momentum in. And VE is equal to the exit velocity relative to the engine. So there's all this stuff of where is the observer of the engine and the plane and everything else. But right now, what we're looking at is, here's the engine. Even though the engine is moving through space, if I'm looking at it from the engine perspective, and I'm here, it looks as if air is going in here. And obviously the exhaust is exiting it. And so it's relative to the engine.